last talk, which is a joint effort by NVIDIA and ShareChat, who performed a very interesting study that investigated the effects of incremental training on neural ranking models. And I'd kind of like to ask the presenters, actually Praveen and Deb, to present. Okay, sorry. That was my timer. Just in time, yeah. That should be number 4. It's a PDF as well. And the full screen, I think, is here.
Okay, awesome. Good afternoon. It's a pleasure to be here. I'm Deb, and I look after developer ecosystems for NVIDIA in Asia. So I'm here to talk to you today about some of the work that we did in collaboration with ShareChat. So right next to me I have Praveen, who was the lead co-author from the ShareChat team. And we'll talk a little bit about the effects of incremental training on recommendation systems. So it's a practical experiment, it's empirical, so I hope you find this valuable. It's probably a good idea to start at the beginning with some of the core challenges that we all know recommendation systems face. And when you think about problems like cold start or concept drift, these are pretty well known, right? When you're talking about the fact that you have a lot of users or items that change, there's a lot of flux in the inventory and user interaction space. A lot of recommendation systems struggle with good defaults unless you hard code or you have a set of learned background defaults. And with concept drift, you're always struggling, especially with situations where there's virality or some kind of seasonal or an external factor that tends to really put a spanner in the works, so to speak. So with incremental training, we're fundamentally looking at solving this problem by frequent retraining. Not of the entire model, but as parts of it. So you'd start with a trained model on all the data you have at that point in time, and then you do frequent, tiny updates as you progress, as your user space is engaged on. For this particular research, we were looking at 3 broad questions. The first one is how often? Right? So yeah, sure, we can do frequent retraining. How often is good enough? What makes sense? Is there an inflection point? The second question was, is there an impact in terms of model architecture? So the features and dataset sizes benefit differently from incremental training protocols. And finally, I think it's an important question to ask, especially in production systems where does incremental training benefit all products or all users equally, or is there a delta here? So it's a great spot, to talk about some of the data that we used for this experiment. Really grateful to ShareChat for crafting a pretty phenomenal experimental data set here. So for some of you who may not be aware, ShareChat is a social media platform for short videos. It's got over 160 million monthly active users and nearly 4.5 billion daily views. So it's a pretty good set to draw from. And in terms of the actual task objectives that the data set reflected, we're looking at 2 events. Primarily whether a user would like the video, and secondly, if there is a watch event. And here a watch event was defined as whether a user does a full watch of at least 98% of the video. In terms of the actual data set itself, we were looking at collecting nearly a month or 28 days worth of user interactions. They were both positive and real negatives for each of these targets. And the negatives were defined as videos that users saw but didn't engage with. So we looked at it. The experiment was conducted on the entire data set as well as a smaller sampled data set consisting of about 1% of all the users. In terms of the actual training protocol, what you're seeing here, we did sort of 2 or 3 experimental protocols. One of them was on a daily frequency spectrum. So you train on the entire 28 days and then you evaluate on the 29th day. Also evaluations done on time-bound frequencies. So at this particular juncture, we're looking at 6 hours where you would train the initial model on the entire data of 28 days, and then you take 6-hour chunks and variations of that. I think the smallest time delta for this particular experiment was 5 minutes. So we try to do it as real time as possible. In terms of the actual experimental setup, obviously, then we are really proud of the NVIDIA Merlin stack. So for some of you who may not have tried, it's an open source recommendation system stack which allows you to take PyTorch or TensorFlow backends and basically deploy them at scale. For the purposes of this experiment, we used 4 A100s with about 40 gigs of memory, and we were using the TensorFlow backend. We also used SOK to distribute the embeddings across the GPUs, and that kind of is a bit of a map reduce when you're looking at orchestrating that part of the pipeline. There's also components like NV Tabular within Merlin, which allow you to define features within a recommendation systems pipeline. For the actual feature sets, there were obviously 3 components. The first one is the ID features, so you're talking about user and item ID and the creator ID, as well as user context. So here you're talking about things like the request hours, the language, any item features as well, so recency, duration, topics, language, etc. And finally, target encoding. With target encoding, the approach taken by the authors in this paper was basically to chunk it in terms of time. So we used a 28 days, all the data up until the 28th day was used to calculate your mean, and then using the smoothing parameter to take your nth or ith chunk. Nothing super, is relatively straightforward, okay? So with that, I think this is a great spot for me to hand over to Praveen, who will walk you through the experiments, the setups, as well as the results.
Thank you so much, Dev, for so basically in terms of models that we experimented with 3 model architectures. First one is MLP, multi-layer perceptron, and you can see that the embedding layer input are basically the ID features, which would be user ID, item ID, and creator ID. The second architecture we tried was DLRM model by Facebook, deep learning recommendation model. This one also has similar embedding tables for ID features, and it has like pairwise interactions. The third model architecture we tried was deep-end cross-network V2 by Google. It has this stacked and parallel cross interaction layers. So these are the 3 models that we majorly experimented with. The first research question we tackled was what is impact of this incremental training on model accuracy, and for this we considered AUC metric, and from the diagram you can see that for both basic ID features and all features, if we go down from training interval from daily to 5 minutes, you can see that AUC improves. For example, for like the AUC for daily training is 0.9109, and if you go down, it keeps on increasing. Similarly, it has similar behavior for watch target as well. Other thing is like we wanted to see how does increment training perform across different sort of features. So you can see that for both basic ID features and even doing like extensive feature engineering, the improvements are there. Other observation that you can see is, let's say I take only the basic ID features and I incrementally train at 30-minute interval. If you see the like AUC, it is 0.9174. And if you do extensive feature engineering with daily training, the basic ID feature with more frequent training is it has like comparable performance. So basically this suggests that you can probably get similar sort of gain by using simpler feature rather than doing complex engineering with more frequent training interval. The second research question we tackled was like, how does different sort of model architecture, does the incremental training gain translate across those model architectures as well? And you can see that we performed analysis on the 3 models that I mentioned before, and the incremental training gains are kind of translate across all of these 3 models. You can see that for MLP on the full data, on the sampled and full data set, we have 0.69% gain when you use basic ID features. Similarly, on DLRM and DCNV2, there are comparable gains as well. The other point we wanted to check is basically the incremental training gains across data set sizes. We see that in our sample data set, the gains are pretty similar to the full data set. So if our sampling strategy was basically 1% random users, so depending upon your sample strategy, you can sample your data set in such a way that your gains basically translate to full data set so that you can basically perform experiments faster. Other aspect we tackled more in the MLP is, let's say in MLP, the third row in the MLP, which is not using basic ID features, you can see that the gain from just using user item context and target encoding features, the gain is 0.13%. But if you just use basic ID features, the gain is 0.69%, which kind of indicates that this incremental training improves the models using basic ID features more. And we will explore that point in the next research question as well. The third research question was essentially, we wanted to see its impact across various sort of user segments, user cohorts, and similarly various sorts of item cohorts. If you see the graph on the left-hand side, this graph is AUC per user activity or user frequency cohort. The users that are on the top are, for example, the green color users. These are very frequent users. And the bold lines are basically daily training. And dotted lines are AUC for hourly training. You can see that the green color is basically very frequent users. Yellow color is slightly less frequent. Red color is even less frequent. And the blue color is the fresh users or the new users. First thing you can observe is that there's AUC gain when we go from daily training to hourly training. There's AUC gain across all these user cohorts. And another point you can observe is for the fresh users, the gain is higher. So the gap between blue solid and blue dotted line is higher than the gap between green solid versus green dotted line. So this is basically like more frequently you retrain, your new users will get better recommendations. If you go to the second graph that on the right side, this is cohort on item frequency. Again, the fresh items are the blue line and very frequent items are the green line. Here you can see that the AUC gains are still holding and they are pretty much consistent across all the item frequency groups. Finally, in terms of conclusion, first is more frequent retraining leads to better accuracy. So you can, there are of course complexities of retraining more frequently. You need better data infrastructure. You need to join your features with your targets more quickly, and also you need to make your training process and inference process better. So of course it has this cost and other engineering overheads, but in general more frequent retraining leads to better accuracy. So you can see whether it gives gain on your data sets. The second aspect is the user and item ID embedding. They are getting higher gains. And these user and item ID embeddings, these are basically very high cardinality features. And these embedding tend to take very high space and memory for your model. So essentially, like, if these, we tried basically some, essentially like these user and item ID embeddings give higher gains. And this is pretty helpful in your cold start problem from both user perspective and item perspective. Third was that depending upon your sampling strategy, relative improvements could be pretty similar. So if you can devise such a sampling strategy, performing your experiments on sample data set can give you quick analysis. And the last point is new and less active users tend to benefit more from this. Thank you.
Thank you very much. So there are a couple of questions here on Slido. What domain did you test on? I think I can answer this as well, so short videos. But also very interesting, were there many new users or new items, and in particular, how did the effect of new user inflow or new user items, how did it impact your results? Could you comment on that?
I'm sorry, I did not get your question.
So in the data set, were there many new items or new users?
So our data set, so basically the Moj app is a short video recommendation. So it has, so in short video, as you see that lifespan of videos is like pretty small. Lot of new content keeps on coming and old content keeps on churning. Same behavior happens for users. So yes, there was quite a bit of newer users and quite a bit of newer items.
Okay. Actually, I was wondering, it seems there is a particular strong improvement when going down from 30 minutes interval to 5 minutes interval. That was 4%, I think, in case of the watching prediction. I was wondering, can this be explained by repeated interaction as well?
Yes.
So it's more likely that a user just, rewatches the same video, and this is captured better when you go down in the time interval?
That is like one, you could say that. Other major thing is like in short video platform, whatever you are watching recently, so let's say you liked some song by Justin Bieber, you are more likely to be shown songs by Justin Bieber, again, essentially. So, or similar content. So your recent watch behavior is very contextual, and this watch target is really sensitive towards your basically recent session or recent actions.
Okay. But were there a lot of repeated interactions in the data?
Repeated interactions, you mean like same user ID,
same user interacts with the same video?
No, there is no repeated interactions.
Okay. There is also one interesting question by Johanna Regenthal. What are your thoughts on when should you do a complete retraining from scratch?
I think like for production, you would want to measure your essentially overall metrics, whatever metrics like you maybe like, whatever metrics is like works for your, and if you see that so for example, if you have let's say half an hour sort of evaluation protocol, you are measuring your metrics over that half an hour, and if you see that your model has drifted quite a lot and those metrics are no longer making sense, you can do some sort of complete cold start again. Sometimes like if you want to launch let's say new experiment itself, you want to add like newer features, that then also you would want to do another cold start.
Okay. Another one.
So Session Chair, I'm wondering if you can give the audience some opportunity to ask questions.
Sure.
Yeah, thank you.
Anyone in the audience?
I'm here. So thank you very much. Very interesting talk. So one question is, for those kind of incremental training or continuous training, usually it may run into catastrophic forgetting issues. Basically, a lot of times when you are trying to learn from those incremental trainings, the model quickly forget about what they have learned from the long-term training. I'm wondering, what have you done to solve those questions for your model training? Did you do something like learning rate tuning or froze some part of your model architecture? Basically, can you share some experience and intuitions on that part? Thank you.
I think like, so since this experiment was done on like offline data set, we did not do like any such analysis on this catastrophic forgetting aspects. We do have like some production model where we take care of such stuff. Maybe we can talk after the call and I can maybe explain a bit more how do we handle that.
Sure.
Thank you so much for the
thank you
great
so much.
session.
Okay, another question. The audience here. Okay, what are your thoughts on whether the benefits of incremental training would also transfer to sequential models?
Also transfer to
Because the models used are quite simple, especially the MLP.
Yeah, I think like we experimented on 3 model architectures and the gains seem to translate across these 3 model architectures. I don't see like any specific hindrance why it should not translate the same for sequence models. I think it also depends on your data set as well. I think I will suggest to probably experiment and see. Mostly it should translate.
Okay, thank you very much.
Thank you so
Again.
much.
Thank you to all the presenters, thanks to the audience, and let's enjoy the coffee break. I would also like to thank the sponsors, obviously. Have a look at the posters if you haven't seen them yet, very interesting. Concludes the session.